So we hope that by playing around with that applet, you were able to see that, in fact, as the number of compounding periods per year rises and rises without any bound, in fact, the amount of money that you have at the end of the year actually levels off. And what you end up with, and you might not have been able to get all of these digits on the applet, but you should end up with 2,718,281, 271828182845 something something something. It almost seemed like it was going to be repeating decimal, right? 1828, 1828, but then 45. So no matter how many times per year you compound it, you'll never get up to $3 million. In fact, you'll never even be able to change this last $1 there to $2, or this 8 to a 9. And if you rounded this up to a 3, you could, but in fact, this 2 will never change to a 3, no matter how many times per year you compound it. So this is a very special number you might recognize. We multiplied it by 1,000,000 so that we would be able to get something that was more than just $2. But this is going to be our definition of a number. So we define the number e to be this limit without the 1,000,000 out front. So the limit as n goes to infinity of 1 plus 1 over n to the n. And of course, now when I don't have that 1,000,000 out front, I have just divided this whole thing by 1,000,000. So it works out to be 2.71828182845. And this is one of these irrational numbers, so there is no pattern to the digits. They don't repeat themselves in any nice way like that. This number first was used by the person who developed logarithms, which we'll talk about next week, Napier, in 1618. And the name E for it was also given by Euler, the fellow that we saw earlier tonight, who gave us the function notation, in 1727, when he was all of 21 years old. So he was doing a lot of very good, important math at a very young age. There is some completely false myth that he chose this number to name it after himself. That is not at all true. He was a very modest, humble man. He would never have done that. Probably more likely is that A, B, C, and D were already in more common use, and E was just the natural next choice. I would just like to take 1 minute to think about what this limit is telling us. There's a couple ways your intuition might say to look at this limit. On the one hand, you might say, when n gets really, 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 really big, 1 over n is basically 0. So I essentially just have a 1 inside the parentheses. And so you're saying the limit as n goes to infinity of 1 plus essentially 0 to the n. But we know that 1 raised to any power is just 1 times 1 times 1 times 1. That should be n. That should be 1. Versus, you might have another intuition, which is that, this thing gets really, really small. But it never quite gets to 0. So maybe you could say, oh, it's something like 1.00001 to the n. Well, what is this? This is a quantity that's growing exponentially. Now, not at a very high percentage, but you're going to let it grow exponentially forever. So when you multiply this number by itself infinitely many times, that's an exponential growth that's just going to go off to infinity. So this limit, if you think about this, is infinity. So on the one hand, your intuition might say that this limit up here should be 1. Or you might say that the limit should be infinity. And it turns out that in this case, somehow, halfway between 1 and infinity is the right answer, 2.71828182845, and it just goes on and on forever like that. So we'll be getting the chance to see this number again, so let's keep it in mind. This is our definition of it. There's a variety of ways to define it, but this is the one that we've chosen. And we'll go on to see many more limits in calculus that will have interesting answers. This is the first one that we've seen.